So today in this class, we'll start with the third theorem, that is theorem 3, which says if f is mapping from a comma b to R, which is a bounded function on P1 and P2. So what are P1 and P2? They are partitions which belongs to the whole set of partitions phi of a comma b. Then they are asking us to prove that L P1F, which is less than or equals to U P2F. P1 is the first partition, P2 is the second partition, which belongs to a set of partitions A comma B. So let us start with the proof. What is that they gave? First write out the given information that f is mapping from A comma B to R is a bounded function. Is a bounded function. Now, where on closed interval A comma B, or you can write f is mapping from A to B is a bounded function. And next, what is that they gave? You got to write this one. P1 comma P2 are partitions which belong to the set, that is phi of A comma B. Okay. Now I'm defining P, let P equals to union of P1s and P2s. I'm just defining P in such a way that P equals to P1 union P2. Okay. That is, what is P actually? P is final. That both P1 and P2, both P1 and P2. We are just defining P in such a way that the unions of P1 and P2 are in P. Okay, now LP1F is less than or equals to LP comma F, and UP2F is greater than or equals to UP comma F. This we have learned from the previous theorem, and we know that this result is from the previous theorem. Okay, and what is that we know? And we know that LP comma F is strictly less than or equals to UP comma F, and if P is less than or equals to UP comma F, what is that we can tell? But from where did we take P? P is union of P1 and P2. So we can write P1 comma F is less than or equals to UP2 comma F. This is from the previous result, like some previous theorem, either 1 or 2. Even this result is from the previous theorem. So from those theorems, we just concluded that if LP comma F is less than or equals to UP comma F, as P is equals to P1 union P2, we can conclude that LP1F is strictly less than or equals to UP2F. Am I clear? Next, moving on to the next theorem, that is theorem 4. This theorem says if f is bounded on A comma B, if f is bounded on closed interval A comma B, and P, there is some partition P which belongs to a set of partitions phi of A comma B, and the small m and capital M. What is small m and capital M? Infimum and supremum. Infimum, supremum of f on A comma B. Then they're asking to prove small m into B minus A is strictly less than or equals to LP comma F, that is less than or equals to, I'll write this in the second line. I'm just asking us to prove m into B minus A is less than or equals to LP comma F less than or equals to UP comma F, which is strictly less than or equals to m into B minus A. What is this? Small m is infimum, this is supremum. What is B minus A? How do you define the length of the subinterval? Delta is equals to B minus A. So that is what they wrote over there. Now look, moving on to the proof of the theorem. What is that? First write whatever they gave. What is that they have given? given that f is bounded on a comma b, closed interval a comma b, and there is a partition p is equals to, how will we define p? A is equals to x naught, x1, so on up to xn is equals to b. This be a partition, of closed interval a comma b itself. Then what is that they gave? They given infimum and supremum, and m comma m are supremums and infimums of f on a comma b. Now we have to define b minus a. That is the rth subinterval. The rth subinterval is given. How will we define subinterval? Rth subinterval IR. IR is equals to xr minus 1 comma xr. Okay, IR equals to xr minus 1 comma xr. And how will we define the length of the subinterval? And delta r. Delta r is defined as the length of the subinterval. This is the length of it. Okay. Till now, I just wrote the given information. Now we are as we are talking about the rth interval, we have to define m and n in r's. So capital MR and small mr are supremum and infimum. Capital MR is supremum and small mr is infimum of what? Of f on IR. Where are we defining? We are defining on R. So what is R? R is the subinterval of the function. So this can be written as m, small m is less than or equals to small mr. That is, the normal infimum is less than or equals to the rth subinterval of the infimum. This is less than or equals to capital MR, and this is strictly less than or equals to capital M for all r equals to 1, 2, and so on up to n. As we have earlier studied, like capital MR is greater than or equals to small mr, or small mr is less than or equals to capital MR. From this result, we concluded this step. This is a very important step. Just remember this one. Okay. So what will we do? We'll just multiply delta and we'll put summation on all the sides. Okay. What is the step that we got? M is less than or equals to MR, which is less than or equals to capital MR, which is less than or equals to M. For all R equals to 1, 2, and so on. Okay. So now multiplying deltas on both sides. So M into delta R less than or equals to MR into delta R less than or equals to capital MR into delta R less than or equals to M into delta R. What are delta R's? Length of rth subinterval. Now summation. Putting summation in all these four. So summation R equals to 1 to N M into delta R less than or equals to summation MR into delta R, where R equals to 1 to N, less than or equals to summation R equals to 1 to N, capital MR into delta R, less than or equals to summation R equals to 1 to N, capital M into delta R. Okay. Now, what is this summation R equals to 1 to N small mr into delta R? LPF. As this is this doesn't have any R, so you can put that out. So M into summation R equals to 1 to N delta R, which is less than or equals to, what is this? This is LPF. LPF, lower Riemann sum, which is less than or equals to, this is UPF. UPF. This is less than or equals to capital M into summation R equals to 1 to N delta R. Why did we write? Since summation R equals to 1 to N, capital MR into delta R is equals to LPF, that is lower Riemann sum, and summation R equals to 1 to N, capital MR into delta R is equals to UPS, that is upper Riemann sum. Okay. From these definitions, we have got this step. In the next step, what is delta R? What is the length? As I've already told you, delta R, that is summation R equals to 1 to N, delta R is equals to B minus A. That is what we are writing. This is the length of the subinterval. length of the rth subinterval. So m into b minus a. This is less than or equals to LPF. This is less than or equals to UPF. And this is less than or equals to capital M into B minus A. This is what we have to prove. Hence, proved. Am I clear? Shall we move on to the next definition? The next definition is upper and lower Riemann integral. Till now, what we have studied, we just studied about upper Riemann sum and lower Riemann sum. Now we are studying about what is upper Riemann integral, upper Riemann integral and lower Riemann integral, lower Riemann integral. So what does this define? Let f is mapping from a comma b to r. Okay, obviously this should be bounded function. This should be a bounded function. Then this f, then in f UPF such that the partition should belong, this P should belong to the set of partitions in A comma B. If you take this, then it is called upper Riemann integral. Upper Riemann. I'm just writing it in the short form. Upper Riemann integral of what? Of this F. Of F on A comma B. And it is denoted as, this is denoted by, this is, as we are talking about the integral now. So how will we define that? Integral a to b bar f of x. As we are talking about upper Riemann integral. So this bar should be for b, upper Riemann integral, f of x dx. Or it can also be written as integral a to b bar f or u f. Okay, how did we write upper Riemann sum? We wrote it as u p comma f, that is partition with the function. Here we are just writing upper Riemann with the function. Okay, that is, this is defined as integral a to b bar f of x dx. This is the actual notation for this. Integral a to b bar f of x dx is equals to infimum of UPF such that P belongs to phi of A comma B. What is infimum? Greatest lower bound. So if you take all the upper bounds and put it in a set, and from that you have to take the greatest lower bound. So that is what the definition of upper Riemann integral says. What is that? Integral a to b bar f of x dx is equals to infimum of UPF such that P belongs to phi of A comma B. Okay. And after this, you will be having lower Riemann integral. The sum, supremum, sorry. The supremum of, what was infimum? Sorry, what was the upper bound? A to B bar F is equals to infimum of UPF. So what will this be? This will be supremum of LPF such that P belongs to a set of partitions A comma B. What is this? This is the lower bound, lower Riemann integral. So how will we denote this? We will denote this as A bar to B, as it is lower. How did we define upper? We took B bar. So integral A bar to B f of x dx, or we can denote this as integral A bar to B f, or we can write L of f. Now we'll define the entire definition. What is that? Integral A bar to B f of x dx is equals to supremum of LPF such that the partition should be in a set of partitions. Okay, what is LPF? The lower bounds. When you take all the lower bounds and put it in a bracket or put it in a set, and you have to take supremum for that. What is supremum? Least upper bound. What is infimum? Greatest lower bound. Okay, So you got to take supremum for that set. Then you'll get the lower Riemann integral. Okay. Let's move on to the next theorem, which is a very important theorem. Theorem number 5. If f is a function mapping from a comma b to R, which is a bounded function, then they're asking us to prove LF is less than or equals to UF. LF is less than or equals to U into F. So what is, okay, LF is less than or equals to U into F. Now what is LF and UF? Upper Riemann integrals and lower Riemann integrals. So before that, we have to just in the proof write down what is the given information. Given that, what is that they gave? F is bounded, obviously. On where? Closed interval a comma b. This is closed interval a comma b. Then we already know from the previous result, what is that? LPF. We are talking about LPF and UPF. So LPF is LPF, that is lower Riemann sum. LPF is less than or equals to UPF, P to F, P1F and P to F. From the previous result, we just took LP1F is less than or equals to UP2F. This is true for each, this is true for each P1 belongs to phi of a comma b. That is that P1, partition 1 belongs to a set of partitions. Now we are talking about UPF, UP2. So what is UP2 comma F? This is a bounded upper bound, is upper bound of set of all lower Riemann sums, right? Lower, see, like from the definition of upper bound, this is the upper bound of set of all lower Riemann sums. So that is what I'm writing it in words. So there is a lower Riemann sum. Now, what is the definition? You have to write the definition. That is lower Riemann sums. As we are talking about the lower Riemann sums, what is definition of lower Riemann sums? A bar to b f of x dx is supremum. That is supremum of set of all lower Riemann sums. Lower Riemann sums. What is supremum? Lower bound, no? So upper bound. Least upper bound. Okay. We are just, see, the reason we are taking like this is because we wanted to prove LF is less than or equals to UF. That is, lower Riemann integral is less than or equals to upper Riemann integral. For that, we are just making use of the Riemann sums. Okay, what is UP2F? UP2F is the upper bound. Okay, that is the upper bound. So what is that upper bound? It is upper bound for the set of all lower Riemann sums. Okay, that is the reason we defined integral a bar to b f of x dx. That is actually a bar to b is a lower Riemann sum. Okay, but what is the definition of lower Riemann sum? It is supremums. I'll just write the definition of lower Riemann sum over here. What is it? A bar to b f of x dx is equals to supremum of all LPFs such that p belongs to some phi of a comma b. Okay, so this is the definition of lower Riemann sum. Lower Riemann integral. So a bar to b f of x dx is supremum. See, this is the supremum of all the lower Riemann sums. The definition, we are just putting it in words. Okay, shall we move on to the next step? Now we just have to write, like, what is all this one? We have to write this one. Okay, one second. So what was the step that we wrote? Integral a bar to b f of x dx is supremum of set of all lower Riemann sums. That implies integral a bar to b f of x dx is less than or equals to UPF2, UP2 comma f. Okay, why did we write this? Because like in words we wrote this one. UPF2 is the lower bound of set of all lower Riemann sums. Okay, so from that, what can we write? We can write this as UP2 comma f is greater than or equals to integral a bar to b f of x dx for all P2 belongs to phi of a comma b. See, why did we write this? If a is less than or equals to b should be greater than or equals to a. So with that concept, we just wrote it like this. What is P over here? P2. As we are talking about P2, that is P2. What is P2? P2 belongs to set of all partitions. Now, we'll take this one. Integral a bar to b f of x dx. What is this actually? Lower bound. This is the lower bound of what? Of set of all upper Riemann sums. Upper Riemann sums. Okay, like this is from the definition of lower bound. So what is that we are writing? This one is the lower bound of all the upper Riemann sums. Okay, now what is that we can write? But what is integral? Like we have to talk about upper Riemann integral. So a to b bar f of x dx, a to b bar f of x dx is infimum of set of all upper Riemann, right? What is a to b bar? What is the definition of upper Riemann? uf is equals to integral a to b bar f of x dx is equals to infimum of all UPFs such that P belongs to phi. Okay, this is the definition of upper Riemann. Now, from this, a to b bar f of x dx is infimum of all the upper Riemanns. Now we have to take this in symbolically. So a to b bar f of x dx is greater than or equals to, once again, a bar to b f of x dx. Okay, why are we writing like this? A to b bar f of x dx is greater than or equals to a bar to b f of x dx. What is this? This is upper Riemann and this is the lower Riemann. So how can we write this? I'm writing it here. U of f is greater than or equals to L of f, or we can write this as L of f is less than or equals to U of f. Hence the theorem.